Welcome back in lecture series on topic electrochemistry. Today in this lecture we will study the relation between molar conductivity and degree of dissociation of weak electrolyte. And degree of dissociation of weak electrolyte is denoted by letter alpha. What is meant by degree of dissociation of weak electrolyte? That we have studied in previous video on, or the first video on ionic equilibria topic. So degree of dissociation of weak electrolyte is the fraction of total number of moles of electrolyte. As weak electrolyte undergo partial dissociation, what happens? The degree of dissociation of weak electrolyte is the fraction of total number of moles of electrolyte that dissociate into its ion when equilibrium is attained. That is called as what? Degree of dissociation of weak electrolyte, and it is denoted by letter lambda. So alpha is equal to number of moles of that weak electrolyte that undergo dissociation divided by total number of moles. That gives you the degree of dissociation. And from that you can also calculate the percent dissociation, that is alpha into 100, that gives you percent dissociation. So that part we have studied in ionic equilibria topic. And today in this lecture we will study what? The relation between molar conductivity and degree of dissociation of weak electrolyte. The relation between these two, that is molar conductivity at concentration C and alpha is equal to lambda C. That is molar conductivity at concentration C divided by lambda 0, that is molar conductivity of electrolyte at 0 concentration. So ratio of these two gives you degree of dissociation. So from degree of dissociation we can also calculate dissociation constant. Degree of dissociation gives you the idea about what? The extent of dissociation of that weak electrolyte. And degree of dissociation, that is alpha, is related with dissociation constant of weak electrolyte, that is K. So consider here a solution of weak electrolyte, that is Ba, and it has a concentration C moles per decimeter cube. And alpha is the degree of dissociation. Then by applying the Oswald dilution law, we get what? Ba in aqueous medium gives you B ions in aqueous medium plus A ions in aqueous medium. This is the dissociation reaction at equilibrium. Therefore, the concentration of Ba, B ions and A ions at equilibrium is what? C into 1 minus alpha. 1 mole, if you take 1 mole, initially 1 mole of Ba, and if alpha is the degree of dissociation, then 1 minus alpha remain in an undissociated form. So here C into 1 minus alpha into, here the concentration of B ions at equilibrium is C into alpha, and concentration of A ions at equilibrium is C into alpha. So substituting these values, we get what? Dissociation constant, that is K, and K is equal to alpha square into C divided by 1 minus alpha. This is the relation between dissociation constant of weak electrolyte and degree of dissociation. Now if this weak electrolyte is weak acid, then K is equal to K. You have to represent it as a K. And if this weak electrolyte is a weak base, then we have to represent it, that is dissociation constant is represented by Kb. So in general it is represented as a capital K. K is equal to, that is dissociation constant is equal to square of degree of dissociation into concentration in moles per decimeter cube divided by 1 minus degree of dissociation. Now you know the relation between alpha and molar conductivity at given concentration and molar conductivity at zero concentration. So if you substitute these values in this equation, that is dissociation constant, relation between dissociation constant and degree of dissociation, then we get what? Lambda C alpha is equal to what? Lambda C divided by lambda 0. So alpha square is equal to lambda C divided by lambda 0 square into C divided by 1 minus lambda C divided by lambda 0, that is the value of alpha. That is equal to lambda C square divided by lambda 0 square into C divided by lambda 0 minus lambda C divided by lambda 0. So K is equal to lambda C square into C divided by lambda 0 minus lambda C into lambda 0. That is the relation between molar conductivity at a concentration C and molar conductivity at infinite dilution and dissociation constant. So using this equation we can calculate dissociation constant of weak electrolyte from molar conductivity of the electrolyte. So by knowing these values of lambda C and lambda 0 and C, we can calculate K, and lambda 0 can be calculated from Coleridge law, that is lambda 0 of cation plus lambda 0 of anion, using that equation, Coleridge mathematical expression. So see here, problem number 1 on this relation, that is the molar conductivity of NH4OH. NH4OH is a weak electrolyte at concentration 0.1 molar is 3.6 Siemens centimeter square mole inverse. Calculate degree of dissociation, that is alpha, of NH4OH at this concentration, that is at 0.1 molar concentration. Molar conductivity at infinite dilution for NH4OH is 271.1 Siemens centimeter square mole inverse. So very simple problem. What is given? Concentration is given to you, and that is 0.1. Lambda C, that is molar conductivity at 0.1, that is also given, and that is equal to 3.6 Siemens centimeter square mole inverse. And lambda 0 is also given to you, that is lambda 0 means the molar conductivity and infinite dilution of NH4OH, that is 271.1 Siemens centimeter square mole inverse. What is asked? You have to calculate alpha at 0.1 molar concentration. Therefore, required formula, alpha is equal to lambda C divided by lambda 0. Value of lambda C is also given, lambda 0 is also given, concentration is also given. So calculate by using this 3.6 divided by 271.1. By using log, we can calculate like this: log of 3.6 minus log of 271.1, and that is what? Log of 3.6 is 0.5563 minus log of 271.1 is minus 2.4332. So this comes to be bar 2.1231, and the log of 1.1231 is 0.01327. Here, as it is bar 2, we have to put decimal point here, that is 0.01327. So alpha is equal to how much? 0.01327, that is degree of dissociation of NH4OH at 0.1 molar concentration. So alpha, that is of 0.1 molar concentration of NH4OH is how much? 1 point in percent dissociation, it is how much? 1.327% dissociation. See the second problem. Molar conductivity of 0.01 molar acetic acid at 25 degrees Celsius is 16.5 ohm inverse centimeter square mole inverse. Calculate its degree of dissociation, that is alpha, in 0.01 molar solution and dissociation constant. That means K you have to find out, Ka. So molar conductivity of CH3COH, that is acetic acid, at 0 concentration is 390.7 ohm inverse centimeter square mole inverse. So what is given? Concentration is given to you, that is 0.01 molar. Lambda C of CH3COH at 0.01 concentration is known, that is 16.5 ohm inverse centimeter square mole inverse. And lambda 0 is also given, that is 390.7 ohm inverse centimeter square mole inverse. And what you have to find out? Alpha as well as K at 0.01 molar concentration. So required formula, that is alpha is equal to lambda C divided by lambda 0, and Ka you have to find out, that is dissociation constant, and that is equal to alpha square into C divided by 1 minus alpha. So using both these formulas we can calculate what? Degree of dissociation of acetic acid as well as dissociation constant of acetic acid at which concentration? 0.01 molar concentration. So substitute the value. Lambda C is equal to 16.5 and lambda 0 is equal to 390.7. So log of 16.5 minus log of 390.7, and log of 16.5 is 1.2175 and log of 390.7 is 2.5979. So this is equal to how much? Bar 2.6256. The subtraction is how much? 6256, and the characteristic is bar 2. So antilog of this 0.6256 is how much? 4223. As here the characteristic is bar 2, we have to write 0 decimal point here, that is 0.04223. So this is what? The alpha. Alpha means a degree of dissociation of acetic acid at 0.01 concentration you got. Now from that you have to calculate what? Ka. K is equal to alpha square into C divided by 1 minus alpha. So alpha is known to you, concentration is known to you. Substitute these values in this equation. So you will get what? 0.04223 square of this into concentration 0.01 divided by 1 minus 0.04223. So that is equal to how much? 4.223 into 10 raised to minus 2 square of this into 0.01 means 10 raised to minus 2 divided by 1 minus 0.04223 is equal to 0.95777. So that is equal to how much? 4.223 square into 10 raised to minus 2 into 2, that means 10 raised to minus 4 into 10 raised to minus 2 divided by 9.577 into 10 raised to minus 1. Therefore it is equal to how much? 4.223 square into 10 raised to minus 6 into 10 raised to 1, that is equal to 10 raised to minus 5 divided by 9.577. So if you take the log of this, then 2 into square of 4.223, therefore 2 log 2 into log of this 4.223 minus log of 9.577 5777. So it is equal to how much? 2 into 0.62 log of 4.223 is 0.6256 minus log of this 9.5777 is 0.9812. So by solving this multiplication we get what? 1.2512 minus 0.9812 and that is equal to 0.2700. So antilog of 0.2700 is 1862, but characteristic is 0, therefore we have to put the decimal point after 1. So 1.862. So that is your answer. K is equal to 1.862 into 10 raised to this minus 5. So answer is what? Dissociation constant of acetic acid at 0.01 concentration, that is equal to how much? 1.862 into 10 raised to minus 5. That is the dissociation constant of weak acid, that is acetic acid at 0.01 molar concentration. And alpha that we have already calculated, it is 0.04223. So like this you can solve the numerical problems based on dissociation constant, degree of dissociation and molar conductivity at a particular concentration or at given concentration and molar conductivity at 0 concentration. So thank you.